Welcome everyone. In this video lesson 1 of Unit 2, we will explore the real number system, beginning with the natural or counting numbers and tracing the development of the number system all the way to the real numbers. As you know, the history of numbers is the history of solving problems. Whenever people encounter the problem that the existing number system could not solve, they extend it by creating a new type of number. In this lesson, you will discover why each new number system was introduced and how they all fit together. Remember, mathematics is best learned through practice, so stay engaged, think critically, and work through the lesson. Let's get started. Like I said, the history of numbers is the history of solving problems people encountered in their day-to-day activities. So, more than 20,000 years ago, one of the main challenges early humans faced was keeping track of how many animals they owned or how many tools they had. And this need to count objects led to the invention of the natural numbers, also known as counting numbers. So the set of natural numbers denoted by capital N, and capital N is described as a set containing 1, 2, 3 up to what? Positive infinity. So these numbers, we call them what? The set of counting numbers, because early humans start counting what? Their objects or their animals based on these numbers. Whatever language they use, they start to count objects starting from what? 1. 1, 2, 3, and up to what? Positive infinity. So the history of numbers begins with the set of natural numbers. We can subdivide this set of natural numbers into different sets based on the property that the numbers contains. Now the first set we have is the set of even numbers. So a natural number, we call it even when it is divisible by what? 2. When you divide a number by 2, if the remainder is 0, then that natural number, we call it what? Even number. Or if it is a multiple of 2, we call it what? Even number. The even number starts with what? 2, 4, 6, 8, in such a way up to what? Infinity. So any natural number divisible by 2 or a multiple of 2, we call it what? Even. And the other part, if it is not divisible by 2, we call it what? Odd numbers. Or we can write odd numbers as twice of n plus 1, where n starts from 0. So when n is 0, you get 1. When n is 1, you get what? 3. In such a way, twice of n plus 1 will give us what? The set of odd numbers. And the other division we have is what? The set of prime numbers. A natural number, we call it prime if it has only what? 2 factors, 1 and itself. So among the numbers, those numbers having factors 1 and itself, we call them what? Prime numbers. So we start with what? 2, because factors of 2 are what? 1 and 2 itself. And factors of 3, 1 and 3. Factors of 5, 1 and 5. So any natural number where the factors are 1 and itself, we call it prime number. And the other is the composite. Composite numbers, if it has 3 or more factors, we call the natural number is what? The composite numbers. 3 or more factors, we call them what? Composite numbers. Now remember, 1 is neither prime nor composite. This is important. We cannot consider 1 as a prime number, and we cannot consider 1 as what? Composite number. Based on the problem faced by early humans from the 5th up to the 7th century, the Indian mathematician began treating 0 as a number. Before treating 0 as a number, just the concept of 0 represents nothing. Nothing or what? Empty. So the set of natural number together with 0, which represent nothing or empty, it gives you the set of what? Whole numbers, which is denoted by capital W, and capital W starts with what? 0. Just 0 represent what? Nothing. Just so far we have whole numbers 0, 1, 2 up to positive infinity. So from the problem of gaining or losing, they define the set of additive numbers. So 0 is the additive inverse of 0, minus 1 is the additive inverse of 1. In such a way, they define what? Additive inverse. So in general, for any whole numbers, a plus minus a is equals to 0. And minus a, we call it the additive inverse of a. So whole numbers together with additive inverse of whole numbers, that will give us the set of what? Integers. So the set of integers denoted by z is a set containing what? Whole numbers together with what? Additive inverse of whole numbers. All this, we call them what? Integers. Now, for this set of integers, we have the following properties. For any integer, a, b, c, by the way, when you say for any 3 integers, by default, this property will be true for the set of natural numbers, at the same time for the set of what? Whole numbers. The first property we have is what? Transitive property, which says a greater than b and b greater than c implies what? A greater than c. This property is always true for any 3 integers. We call it transitive property. If you know for sure a is greater than b and at the same time b is greater than c, then this implies a must be what? Greater than c. So this is true for all what? Integers. And we have also additive property, which says if you know a is greater than b, then adding the same constant on both sides will not change the inequality. That means if you add both sides c, a plus c will be greater than what? B plus c. This property we call it additive property. And we have also the multiplicative property. We have also the multiplication property. For positive c, a greater than b implies ac greater than bc. Now this is important property. Later on, when we solve inequalities, we are going to use this property. Now if you multiply both sides with positive integer, the inequality remains the same. But if you multiply with negative, for c less than 0 means c is negative. So if you multiply an equality based on negative, both sides with negative, we need to change the inequality sign. So a greater than b implies ac less than bc because we multiply both sides of the inequality with what? Negative number. So these two are multiplication property for what? Any 3 integers a, b, c. And the fourth property, given any 2 integers, one of these 3 must be true. We call it law of trichotomy. One of these 3 means given any 2 arbitrary integers a and b, one of these 3 must be true, meaning a greater than b or a is less than b or both are what? Equal. So these are the basic properties of integers. Still, the set of integers will not solve every real-life problems. Because of that, they define the set of rational numbers. So the way rational numbers are defined, which is denoted by Q, a set containing A over B, where A, B are what? Integers, provided B is different from 0. So any integer over non-zero integer will give us what? A rational number. We can also call A over B as what? Fraction, provided B different from 0. So 4 over 15, for example, this is what? A rational number. We can call this also what? Fraction. Proper fraction. Because the numerator is less than what? The denominator. So whenever we have a fraction having numerator less than denominator, we call it what? Proper fraction. If the numerator is greater than the denominator, we call it what? Improper fraction. So for rational numbers, A over B, we can call them also what? Fraction. Proper or what? Improper fraction. Just keep in mind, we can rewrite improper fraction as a mixed number. For example, 20 over 3, that is the same as 6 and 2 over 3. Because 20 by 3, we have what? 6. The remainder is 2. So 6 is the quotient and 2 is what? The remainder when you divide 20 by 3. Yes, later on we'll see this concept in the division algorithm. When you divide 20 by 3, the quotient is 6 and the remainder is what? 2. That means we can write this improper fraction as a mixed number, 6 and 2 over 3. So these are important concepts regarding the rational numbers. Remember, in any rational number, A over B, when you convert it to decimal, it can be terminating. That means the digit after the decimal point will terminate, or it can be a repeating decimal. The digits after the decimal point will repeat, one of the two. Now, if you have a decimal which neither terminating nor repeating, we call it irrational number. For example, if you take a decimal D, 0.121122 in such a way, this is what? Neither terminating nor what? Repeating. So such decimals, we call them irrational numbers. Even root 2, root 3, root 7, these numbers are also irrational number because they are not rational. In the coming lesson, based on proof by contradiction, we will show these numbers are irrational number. In the area of a circle and the circumference of a circle, we have important number pi, which is neither terminating nor what? Repeating decimal. E is also what? Irrational numbers. So these are good examples of irrational number. So rational plus irrational, we will get what? The set of real numbers. And the way we define real numbers, the set of real numbers contains x, says that x is a rational or what? An irrational number. So the union of rational and irrational will give us what? The set of real numbers. So this is the history of numbers. And again, for the set of real numbers, we have the following important properties. Given three real numbers ABC, the set of real numbers is closed under addition and what? Multiplication. Even it is also closed under subtraction. Closed under addition and multiplication means the sum of two real numbers will give you what? Another real number. Such property, we call it what? The closure property. And the product of two real numbers will give you what? Another real number. And we say the set of real numbers are closed under what? Multiplication. And addition and multiplications are what? Commutative. For commutativity, a plus b is the same as what? B plus a. A times b is equal to what? B times a. Because of that, we say addition and multiplication are what? Commutative on the set of real numbers. They are also associative. Associative means for addition, a plus b plus c. Whether you add first b and c or a and b, whatever the order, the sum will give us the same result. Similarly, the product will give us the same result. A times b times c or A times B times C, both will give us what? The same result. Such property we call it the associative property. Yes, these are the basic properties we can discuss for the time being. In the coming lessons, we'll see additional properties. Just 0 is additive identity or unit element of addition. Like we discussed before, any number plus 0 is the number itself. So we call 0 is unit element of addition, or we call 0 additive identity. And 1 is unit element of multiplication, because any number times 1 is the number itself. And every non-zero or real number will have a multiplicative inverse. That means 1 over A is the multiplicative inverse of A, or A is the multiplicative inverse of 1 over A, because the product gives us what? 1. I hope after this lesson you will have a clear understanding of history of numbers. In case you didn't subscribe my channel, please subscribe to the channel and turn on the notification bell so that you won't miss the upcoming lesson. Thank you.